I have your homework to get back to you. And I sent the key out on email last night. So, just like the exam, you'll have the key, you can go back through the homework problems, see what we were getting at, what we wanted, things like that. Okay, equilibrium. Now, equilibrium is intuitively what it sounds like. You have two things that are,
Balance.
they're balanced. So think of it, two heavyweight fighters that are roughly equally matched. Irreversible reactions. So reactions where the free energy change is of such a large magnitude that surmounting the activation energy going backwards would be,
Same.
just insane, right? Is not what we're dealing with. We're dealing with things here where the forward activation energy and the reverse activation energy are not all that different from one another, so there's not that big of a free energy change. And as we're going to see with thermodynamics, why this actually works has to do with what's driving the change, okay? You have two components, enthalpy and entropy. Well, you could have something that is thermodynamically favorable, but yet it just doesn't proceed very well simply because it may have a substantial enthalpy or heat change, but the net entropy change, it may actually require more order to do it, and you gotta see which one wins out. But for now, with equilibrium, right, we're gonna be dealing with reactions that go forward and backwards. Now, that may seem like, oh God, now we gotta do what? No. There's actually a good thing about this that is going to make some aspects of this a good bit simpler. In that, I will tell you right now, with equilibrium, you don't have to deal with doubling tables. All you gotta deal with is the balance equation. We'll talk about why in just a minute, okay? But equilibrium is exactly what it sounds like, right? The forward reaction and the reverse reaction are proceeding at equal rates. And so let's look at this. Now, I could not find the symbol on the computer when I typed this. But generally in your textbook, equilibrium is going to be represented by those two half arrows, one going to the right and one to the left. This is otherwise the same generic reaction that we dealt with when we first started dealing with rate law. But what was the emphasis with rate law? We emphasized that you could not use the coefficients of the balanced equation unless the equation presented was also either the complete reaction, in other words, it was the exact mechanism, or it constituted the rate determining step. That was the only two times, which is not common. Okay? Equilibrium, on the other hand, is a little bit different. We got the forward reaction, we've got the reverse reaction. Each one has its own rate constant associated with it. And so we can break this thing into pieces. Right? Now there's some things we need to recognize here. One, the concentration, when it's at equilibrium, right, the overall concentrations of the products, of the reactants, is no longer changing because the forward rate is balanced with the reverse rate. Right? And so whatever this gets converted to products, there's an equivalent amount coming back. Okay? Now, the concentrations of the products will be constant at equilibrium. That does not imply that there's not anything going on. right? This is what we call dynamic equilibrium, right? As opposed, static equilibrium is when static equilibrium is what you have in physics, when you have no net forces acting on an object. Dynamic equilibrium, we still have stuff in motion. We still have reactions happening, but neither the forward nor the reverse reaction can gain any ground. All right? And so think about it, when you get into I don't know how familiar y'all, but I don't watch it. The closest I come to being a boxing fan was the Rocky movies. Anyway, but, think about a late round, 14th, 15th round boxing match. More than likely, this thing is going to end on a decision of the referees. Because at that point, they're more or less in equilibrium with each other. If they've gone that long, all right, neither one is likely going to be able to gain enough ground to win out, unless they get some lucky shot in. That's the general idea here. Neither one can gain any ground. We still have the forward reaction going. We still have A and B turning into C and D. The difference is that the backward rate is in equilibrium, and so any amount that comes forward, there's sufficient amount that goes backwards to reverse the process. Now, this does not imply that the concentrations of the reactants and the products are equal to one another. Equilibrium can lie substantially either forward or backwards of the equivalence point of concentration. It's not a 50-50 split. About the only time we see that is in strong acid, strong base, where this thing goes to completion. With this, though, the concentrations of the products and reactants are they're typically not the same. You see a lot because concentration is going to be governed off of the coefficients. And it may very well be that you have far fewer moles of products than you do reactants, which is going to drastically alter the concentration. Yeah.
So you can have different amounts of it, but they have the same forces pulling against each other, is what you're saying?
Essentially, yes. Right. Let me emphasize this. Depending on the values of these coefficients, right? Let's say that this is all in a 1 liter container. Right? And whatever these species are, when I balance up, this is a 3, this is a 4, this is a 2, and that's a 5. Okay? Whatever those concentrations happen to be, let's assume that we're dealing with initial, right, even molar concentrations here. These ratios are in moles, right? And so if I start off with 3 moles of this and 4 moles of this in that liter of solution, then the concentration of A is 3 moles per liter, right? Mm-hmm. The concentration of B is 4 moles per liter, or 3 molar and 4 molar. There would be some net shift here, but two molar, 5 molar. Okay.
So do the moles have to add up to be the same on both
No,
sides?
no. Mass does. You have to have the same amount of mass, law of conservation of mass. But you do not have to have the same number of moles. This is more apparent in gaseous systems. When we talk about gas laws, we're going to see that it's going to be an extension of a principle we're going to talk about today. Reactions don't necessarily produce the same number of moles from one side to the other. Consider this one. Right, so 2 moles of hydrogen plus 1 mole of oxygen. All of these in the gas phase. will give you 2 moles of water vapor, okay? 3 moles are reacting to produce 2 moles. So the molar count can go down depending on what gets bonded together and what gets broken. However, the mass of the hydrogen plus the mass of the oxygen has to add up to the mass of the water, okay? And as we see when we start talking about system stresses, there's one of the formulas deals with, if I stress it on one side, it'll shift to the other in order to relieve the stress. Okay. In particular, if I compress the volume, it will shift to relieve the stress to the side that has fewer moles of gas, because fewer moles, lower volume. If I expand the volume, it'll shift the other way. And there's a whole principle, and it's the driving principle in biology that we're fast headed to. But no, the mole count does not have to be the same. The mass conservation does. All right. When dealing with equilibrium, this is where all of these, so far we've only dealt with one K value, and that was lowercase k, the rate constant. The rest of them are going to be equilibrium constants, and the different versions depending on what you're doing. They're all based off of this, and let's see here. Now, at equilibrium, if you were to break down the forward process into its full mechanism, and then the backward process into its full mechanism, combine all the equations algebraically, you're going to be left, right, a lot of it's going to cancel, and you're going to be left with 2 very important steps. You're going to be left with the forward rate determining step and the backward rate determining step. What did we say about rate exponents if the equation was solely the rate determining step, or you had the rate determining step? You could use what? Instead of having to go through and use a doubling table, you could just pull the exponents straight out of what? The coefficients of the balanced equation. Well, at equilibrium, basically all you're left with is the forward rate determining step and the backwards rate determining step. Meaning, when I write my equilibrium out, I can just use what? The coefficients of the balanced equation. I don't have to go through all the doubling table stuff. You could, but it's going to come out the same. So here, my forward reaction rate forward is going to be equal to K times concentration A raised to little a, and concentration of B raised to little b. Our rate in reverse is going to be its own, all right, this would be KF, this would be KR, right? K forward, K reverse. Is because in the reverse reaction, what becomes my reactants? C and D. All right, the products of the forward reaction are the reactants of the reverse. And so this will be C raised to the little c and D raised to the little d. What do we know about this? At equilibrium, what's the relationship between those two numbers?
Equal.
They're equal to each other, meaning that K forward, the expression for the forward rate is equal to the expression for the reverse. Now, no calculus on this one. Straight algebraic manipulation. ratio of K forward to K backwards or K reverse is going to be, so divided K over here, and then I'll divide these two over here. So, let's form the bottom of the page. This is the equilibrium constant. Which is more commonly termed products over reactants. Because you never see it written as this ratio, you just simply see that, right? These are the products of the forward reaction, these are the reactants of the forward reaction, because it's expressed forward to reverse, okay? You could, products over reactants, right, when dealing with the forward. That is the equilibrium. Now, KEQ is a generic term, right? It's like different types of eggs, right? If I say go buy an egg, that's actually not enough information, okay? Do I want small, medium, large, or extra large eggs? Right? Do I want free range, organic, or, Sanderson Farms? Whatever the case may be. There are different types of eggs, okay? Equilibrium constants are a whole category of constants. Depending on what we're doing is going to determine which one we use, all right? That could be Ka, which is the dissociation constant for an acid, or Kb, which is the dissociation constant for the base. So, here's a thought, are those likely to be mathematically related to one another? Yeah, because acid, where you find acids, you typically find bases, right? All right. Kw, all these actually are the whole group, which is the autoionization constant for water. Right? Water will, to a small degree, ionize on its own. It'll react with other water molecules and then recombine. Very, very, very small. But these two are distinct opposites of one another, and they're connected by that one. So it's a whole group of them here. Whether or not something will dissolve or not is dependent on KSP, which is solubility product. And we're going to deal with those when we get to solutions. We're not quite ready yet. But this is a generic term. You don't see, beyond chemistry class, at least initially, people saying, well, the KEQ for this is, no, they'll tell you the Ka, or the Kb, or the KSP, or something like, whatever the context is of what they're doing, that's the equilibrium constant they're going to use.
Why, when you put Kf over Kr, why?
The ratio,
So you revert, so Kf is equal to A and B, and Kr is equal in the reverse, but.
Let me phrase it this way. Part of it is basic axiomatic definition. We could have developed it with the flip side, Kr to K forward. But it would have reversed everything in the interpretation. The fact that we built this thing as the ratio of K forward to K backwards is simply a matter
Based on the reverse reaction
of directional designation. All right, for the equilibrium. We could have defined it the other way, but it would have reversed the meaning of everything that we are about to talk about. Because the equilibrium constant tells you a lot about this thing. It tells you specifically what you're gonna have more of when these rates balance out. If it's exactly equal to one, when you do this here, then that tells you that the equilibrium lies dead on in the center. And that is the one time that you would have equal amounts of products and reactants. We don't see that all that often. What you usually find is KEQ is either greater than one, all right? If I have way higher concentrations of products than reactants, this creates a top-heavy fraction. Top-heavy fractions are greater than one. So conversely, if I see the KEQ is greater than one, or if I see my equilibrium constant is greater than one, whichever one it happens to be, then I know that the concentrations of my products exceed the concentrations of my reactants there, and the equilibrium shifts toward the right. The reaction favors the production of products in this case. Yeah.
Okay, so on here it says the K of over KR, so like, I'm confused because KR is the CD1, right? So we have it on the bottom?
Do the divisions. Do the divisions explicitly. If I divide by KR here, right, it cancels out. With that.
Oh, okay.
Now, I've got to get this part by itself, which means I've got to divide by this. And that's how it ends up.
Yeah, that's what I was asking.
So it's not equal to each other, it's just like.
Correct. It's a ratio.
Okay.
Is a product always reverse, right? And the reactant always forward?
As far as what? You have to be careful with this. Now, once we do the derivation, we simply reference it in relation to the forward reaction. Products, reactants.
Okay.
Right.
And what's the KSP mean?
That we'll come to it, don't worry about it.
Okay.
The fact that those are just examples that I was using to illustrate that KEQ is an entire class of equilibrium constants.
Oh.
All right.
So if it's greater than one, then the products, there's
This,
more
the
products.
products are favored, yes. The reactant is going to produce, even though the forward and backward rates are equal, that's at equilibrium. They've reached a point that they're undoing each other, but that might not occur until a larger amount of products has been produced, okay? If it's less than one, then the reactants are favored. Let's talk about this from a very specific example. So let's take all right. That's acetic acid, vinegar. This proton right here, right, and this is a classic organic formula. This proton right here is acidic. Right? Not highly acidic, but it is. Let me write out the expanded structure. There you go. All right. That proton is acidic. Now, with acids and bases, okay, weak acids, they will degenerate into proton, which combines with water, right? And the appropriate conjugate base. let's think about what this is telling us, okay? If and this would be a Ka, okay, an acid dissociation constant, but it is nonetheless an equilibrium constant. It tells you what the relationship is, right? Now, the Ka for the dissociation of acetic acid is 1.8 times 10 to the minus 5, right? So is that larger or smaller than 1? Smaller, way smaller. Let's think about what that tells us. In an aqueous environment, this thing will dissociate. Now, water does not appear, right, as solvents, right, do not appear in the equilibrium because they are not direct reactants, okay? Solvents are typically pure substances that the concentration is considered to be way excessive. The concentrations are taken to be absolute 1, and they factor out. Let's think about what this is then. If I ignore the water, then there should be only 3 things in this beaker. So if I go to the grocery store, I get a bottle of vinegar, which is acetic acid, I pour some of it in a beaker, and then I fill it up with water. And I go through there, and let's just say the technology existed for me to go in and individually count, right, these things. What is this telling me? What am I going to find the majority of? Right? Look at your equilibrium constants. We've already established that it's way less than 1, meaning that at equilibrium, the reactants are favored. What this means is that in that beaker of acetic acid and water, if I could count them up, I'm still going to find that the absolute vast majority of the acetic acid molecules are undissociated. They're still in this form, not this form, right? And that makes sense because we know that this is the business end of an acid.